and record this. In the schematics I've been reviewing, okay, I've been seeing a couple common errors that I want to address. I'm not going to pull everyone's schematics up here because that would just be a violation of everyone's privacy. So if you've done what I'm going to draw out, you don't have to say anything if you don't want to, and I'm not going to call anybody out on it. So one of the biggest problems I've been seeing with schematics is that we're forgetting the required parts of a circuit. Okay, so I've seen a couple schematics drawn. Let me just throw in some lines here. And throw a bulb in. Okay, I've seen a couple schematics drawn where you've put the bulb in and then you've put a switch in. Okay, and you've drawn a schematic that looks somewhat like that. Can anybody tell me what the problem with this schematic is?
The switch won't control the light.
Yeah, switch won't control the light, but what's the bigger problem?
No labels?
Not a complete circuit.
If I close the switch, what's going to happen?
Nothing.
Oh, something will happen.
You'll have a direct.
Say that again?
It will short the circuit.
It's a direct short circuit.
Shut off the light.
Yeah, if I close this switch, I can guarantee this light bulb is going to go out, not because of the switch being closed. The switch being closed will blow the breaker that's on this circuit or blow the fuse. So when you're looking at any schematic before you turn it in or before you wire it, you want to make sure that every leg or every rung of a schematic has a source, which is your line and neutral, a path, which is the wiring, some sort of switching device, and a load. Okay, so this schematic would be right if that was there, okay, and if I didn't have any wires there, okay? So again, every schematic, every rung of a schematic must have a source, must have a path, must have a switching device, and you must have a load. Okay, without any of those, your schematic is not quite correct. Okay, the other thing that I saw some people doing more, especially on the hand-drawn schematics, and overall the hand-drawn schematics are looking really nice, but what I saw a couple people do, and I've been seeing this for years, so this isn't anything new, okay? You've done that and I know this is by accident, so you're taking something that has a rectangular shape and you're drawing around it to get the base of your schematic. What's wrong with this circuit?
Same thing as before?
Yeah, basically the same thing as before, okay? You're going to have a direct short circuit, so this schematic would not work. So again, if you're drawing these schematics and using a rectangular piece of cardboard or something to draw around, or your phone or something like that, erase that bottom line for me. Okay, so those are two small issues with schematics that I saw. Okay, again, just be careful of that. Because again, I know it's an accident. I know it's not that you don't know what you're doing. I just know it's an accident thing. So, any questions on schematics before I move on?
No, sir.
Okay, let us talk about electrodes. Okay, so the whole purpose we're doing of the oil burner, we have one purpose, okay, and that's basically to create fire in a way that we want fire to be created. Okay, so we have our air, we have our oil, okay, and now we need to create heat to A, ignite the oil vapor, and B, to keep it burning, okay? So our initial heat has to come from the electrodes. Okay, now electrodes are connected to a 10,000 volt or a 14,000 volt transformer. We're going to talk about the transformer in a minute. So let's talk about the electrodes first. Okay, they're very much like spark plugs of a car. Okay, I showed you a picture of this last week, but they're very much like spark plugs of a car. They're connected to the ignition transformer through a short run of high voltage wire or by the springs that are on the ignition transformer. Every electrode is encased in a ceramic insulator. The electrodes are held in place by use of a bracket that allows them to be moved for proper adjustment. So if I go back to the prior screen, okay, here's my ceramic holder of the electrodes. Okay, so we have the electrodes. It passes through the ceramic holder and then comes into my connections on the back end of it. But the ceramic holder is extremely important. This is where it clamps into the burner. Okay, so the ceramic has to be intact because they're held against metal. They can't be cracked. You don't want to tighten them down too far. So when we look at the complete electrode nozzle assembly, right here is where the electrodes are held in place. Okay, and the tips of the electrodes come out here into the path of the oil, because right here is where my nozzle gets put. Okay, so we clamp the electrodes in. This is a clamp that you can loosen and tighten in order to turn and adjust these electrodes. Okay, you're going to spend a lot of time on electrode adjustment in shop, and occasionally you're going to want to toss one across the room because they're tough to get adjusted. Okay, there's an art and a science to adjusting these things. The ceramic insulators on electrodes have to be clean. They can't have any cracks in them, or the spark will leak and short to ground. So again, when we look at this, if I have any cracks in this electrode at all, if there's any damage to the ceramic, okay, I have a chance of that spark, instead of coming out where I want it to come out, and that's between the 2 points of my electrodes, I have the chance it's going to come out and it's going to short to the metal back in this portion or in this portion of it. Okay, so the electrodes have to be clean, and the ceramic has to be clean, and it cannot have any cracks in it. The ceramic can be cleaned with a good degreaser and a clean rag. Okay, if this furnace is maintained, if this burner is maintained regularly on a yearly basis, you don't have to use major like sandpaper and everything else to get the electrode ceramics clean. Best degreaser that I've ever found for cleaning electrodes and nozzles and nozzle assemblies, believe it or not, is lacquer thinner. You can buy it in the paint aisle of Home Depot or Lowe's. Okay, lacquer thinner is probably the best cleaner I've ever found to remove the garbage from this. So again, ceramic insulators. Now, what's wrong with this set of electrodes? There's a problem with this set of electrodes already. Can anybody see it? Hey guys, it's okay to answer with a wrong answer. No one's going to beat you up for it.
I have no idea.
Looks like someone.
I don't think they're the same size.
What was that?
The size of them look different to me.
The size isn't the. I'm more concerned about the tips.
Look worn, like someone touched them.
Thank you. These are not new.
Yeah, they is worn.
They're worn down. New tips will actually come out to a point. Okay, they have a really pointed end on them. So these tips are actually worn a little bit. Actually quite a lot. So this is something that when the tips get to this point after a couple years, and it looks like, these don't look like shiny metal, even though the picture's not all that great. As these tips wear down, sooner or later you have to replace the electrodes. They're universal. They're not tough to replace. So again, ceramic can be cleaned with a good degreaser and a clean rag. Any cracks or chips in the ceramic insulator that you spot cannot be repaired. Don't try to be Johnny Fix-It and repair electrodes. You can't do it. Crazy glue won't work. That's something homeowners try on occasion. You must replace the electrodes. Okay? Any damage to the electrodes, just replace them. It's not worth the headache you're going to have about callback after callback after callback if you don't replace them. Electrodes have to be adjusted properly to fire the unit correctly. To do this, we use what's called an electrode adjustment tool or a gauge. Okay, most often you're going to use a gauge. Okay, there is a Beckett gauge. Okay, that you'll get when you get back onto campus. Okay, you're going to get as part of your shop. It's a little triangular sort of, well, not really triangular. It's this portion inside my drawing right here. It's a metal gauge. It's put out by Beckett, okay, which was one of the burner manufacturers. Your electrodes, when you're looking at the set, when you're looking at a side view, this is a side view of your oil burner. When you're looking at a side view, your electrodes have to be a certain amount of, this is the center line that I just drew in there. My electrodes have to be a certain distance over the center line. That's to keep it in the cone of the oil spray. Then you take a look at then you put this between the two electrodes, and the electrodes have to line up to that line and that line. So we're talking about 3 measurements of electrodes. Okay, we have the distance above the center line of the nozzle. That's how high they are. We have the distance between the 2 points of the electrodes. And then we have a distance of how far out in front of the nozzle it is, which is that line right there. So there's 3 electrodes lines. Now, when you're holding this nozzle in your hand, when you're holding this whole oil nozzle assembly in your hand, this is what takes practice. Okay, because you have to hold this adjustment gauge. You have to move the electrodes, which you have a loosened screw on, okay, to be able to move them, and you have to hold this whole assembly. And you only have 2 hands. So again, this takes some time and practice to figure out how to adjust. I'm just introducing the concept here. You're going to be doing this more when you get into the shop. Okay, you're going to practice this. And again, I guarantee by the time you practice it, you're going to want to toss this thing across the room someplace. Don't. Okay, there's oil burner techs in the field that still get pissed off at electrode adjustments. So, but one tool does it all. And this gap between the 2 points can be a 1/16 of an inch all the way up to 1/4 inch. Okay, so you have very small measurements. Now, when we look at a nozzle assembly, okay, when I go back and look at a nozzle assembly, which is this one here, this whole thing is the nozzle assembly. If my electrodes are too far apart, what's one of the possible errors that I'm going to see? What's going to happen if those points are too far apart?
The sparks can't connect.
It's not going to spark properly, right? So with my oil, I'm continuing to spray oil into the combustion chamber. Okay, so I now have oil pooling at the bottom of the combustion chamber. What's going to happen to that oil eventually when it starts to heat up enough if I finally get fire in there?
It'll evaporate and boom.
But it might not. Yeah. It's gonna eventually have an uncontrolled combustion in there. So it's very important that these igniters be lined up properly. Okay, so that's my whole key on these electrodes. They have to be lined up the certain distance above the center of the nozzle, distance apart, and distance in front of the nozzle.
I have a
Do me a favor. I'm going to mute everybody. If you have a question, unmute yourself.
I have a curious question.
Yeah.
Going back to the electrode tips, when they're that worn out, like the picture showed.
Let me go back to that picture.
Yeah, that one. What happens to the spark? Does it change the spark direction? Does it?
You're not going to have a. Well, two things happen when you're first of all, if you don't catch that these have worn out, okay, like they have. If you don't catch that they've worn out here, the distance between the tips is starting to get wider, okay?
Okay,
So
I get you now.
I'm going to have a weak spark. Now, when you come in to adjust this, if you came into a service call where you had to adjust these back into place, it gets very difficult to get these two corners, like right there and right there, to be the same correct distance apart.
Right.
Okay, so because you have to actually bend it. Okay, so you're going to put a pair of pliers on this right here, and you're going to have another pair of pliers here, and you're going to have to attempt to bend these into the right positions. That is very difficult to do without breaking the ceramic.
Okay. I get you now. Thank you.
Okay. So the ignition, the separation of these electrodes is very important. Any other question on the electrodes? I mean, they're simple devices, no moving parts. Okay. I think that takes care of the electrodes. Just be careful with them. Don't break them. That's the key on electrodes. Be careful with them. Don't break them. And again, clean the better. Okay, we talked about two types of transformers briefly last week. What are my two types of transformers?
Ignition and solid state.
And that's what we're going over today.
Step down, step up.
Step down and step up was what I was looking for. Okay, so our step down transformer takes our power and goes from my 120 volts to 24 volts. My step up transformer takes my power and goes from the 120 volts to the 10,000 or 14,000 volts. Now, more and more on oil burners, we have two types of ignition systems out there. We have the traditional transformer based, but now we're starting to get more and more solid state based that uses solid state components like circuit boards and stuff like that to provide that spark. So I want to talk about the traditional transformer based first. Okay, because these are still what you're going to see most often. Okay, so our ignition transformers are different than the solid state transformers, but they are a lot of times interchangeable. Okay, this is a picture of an ignition transformer. Okay, the two leads over here. Okay, the two leads up at the top here. That's what tie into neutral and our primary control, which we still have to talk about. Okay, neutral and primary control. Only two wires. Does it matter which goes to which? Not really, because we're talking AC current. I have two springs here. Okay. When this folds over and seals up onto the burner, these two springs are touching my electrodes. Okay, they're touching the long metal piece that comes out of the back of the electrode. Okay, and they have to make firm contact. Over time, these springs will wear out. Okay, as most springs do over time. When they don't make good contact anymore, you have to replace the springs. Your transformer will burn out before that anyways. So a step-up transformer, as I just said, changes input voltage to a higher output voltage. In oil, we're changing 120 volts to a 10K or 20K okay, spark. You don't see 20K that often on oil. This would be like heavier commercial. We're most often talking 10K. That's 10,000 volts. Solid state components I might have in the middle here someplace. Okay, 14,000 on up. So again, 120 to a 10,000 volt. Okay, now, older style transformers, we can check using a screwdriver. Okay, you do not want to do it if you have a solid state transformer. So again, see my warning labels all over this slide. Old style transformers. These are big black metallic boxes that look like that. Okay? So I'm going to tell you how to check those. For newer style transformers, you do not do this. Okay? You take an insulated screwdriver with a running transformer, a transformer that's powered, and you put the insulated screwdriver on one terminal of the transformer, and you put the blade not directly on the other pin, but you put it near the other pin. Okay? And you should see a spark if the transformer is working properly. What could go wrong with this idea? Why do we give all sorts of warnings about this? Anybody?
You can get a shock.
Yeah. What about if you're near anything explosive?
Even worse. Boom.
Yeah. Okay. You're going to see oil burner technicians, when you work as an apprentice with somebody, you're going to see this method done quite a lot. Guys, do so at your own risk. Okay? And it works. I've done it. Okay? But I've also seen someone grab a screwdriver with wet and sweaty hands and do this method and get a very bad shock. 10,000 volts will knock you on your butt. Okay? It's not a lot of amperage. It won't kill you, but it will knock you on the floor. Okay? You'll throw the screwdriver, probably hit the homeowner in the head or something like that. So just don't do it. Okay? So the best way to check this is they make what's on, actually have, you can buy it at a local supply shop. You can actually buy a transformer checker. It's equivalent, it's like your voltmeter, and you can actually clamp it onto the leads, and it will tell you if the transformer is good or not. Okay, you can also ohm out ignition transformers. If you unplug this, you take your ohm meter, go between the two pins of the secondary. Okay, take a reading. You should have some number. Go between the two lines onto your primary. You should have some number. Okay, other than 0. If it ohms out properly, your transformer is good. Okay. Transformers last a long time. 9 out of 10 times you never get a bad transformer. It's something else causing the problem. So, again, screwdriver method, you're going to see technicians use it. I think we actually do have you do one in the shop just to basically so you're aware of how it works, but it's not something you want to do frequently because it's too easy for you to get a screwdriver that has a cracked handle. It's too easy for you to touch this metal part while you're doing it, and it's just not a good idea. Questions on that?
Negative.
Okay. Now, those are the old style transformers. There's not much more I can say about them. Okay. Igniters, okay, are similar to a transformer. And we're going to have a brief slide set on that as well. But igniters works with solid state materials. Now, the important part about the igniter and the reason we do it is during the ignition sequence, it provides more sparks per second than the transformer does. Okay, the transformer is going to provide a solid spark. Okay, but the igniter provides more sparks per second, and they are designed to come out of the circuit following ignition. Okay, the old style transformers, they're heavy. They're designed to run constantly while the burner's providing heat. While the burner's firing, the old style igniters, the old transformers, are going to run constantly. You will have a constant spark. The solid state igniters will not run constantly. They come out of the circuit once flame has been established. We can check the operation of the igniters much more easily than the old style type of igniters. Okay? So the way we do this, we tested with the spark method. We disconnect the power. Okay, whenever you mess with an ignition transformer or igniter, disconnect the power. You lift the igniter to the full open position and you set the clips to about a 1/2 inch or a 3/4 inch gap. You energize the igniter and you check for a spark. If the spark jumps, the igniter's good. Can you ohm out a solid state igniter? Do you have coils in there? Just go ahead, guess. If you don't know, it's fine.
I don't think so.
No, you won't have coils in a solid state igniter. Okay, so ohming out will give you numbers that make absolutely no sense whatsoever. So this is the best method to check. Okay, now you can ohm it out, but you actually have to go to ground. Okay, you cannot go between the two terminals. With the power off, ohm a high voltage lead to ground. Then ohm the second high voltage lead to ground. Notice I'm not doing between the two high voltage leads. If the ohm readings are within 10%, the igniter's good. But again, you cannot take an ohm reading from lead to lead. You don't have a coil between the two. You got to go to ground. Okay? This burner, does it have a traditional non-solid state, or does it have a solid state on it?
Solid state.
It's a solid state. You see, it's a little bit of a lower profile. Okay, it's not one of those big square boxy looking things. So this has a solid state transformer on it. The transformer connects in regardless of what type of transformer we're using. It connects into some brass leads or brass connections, okay, on the back of the electrodes, or it uses a spring that clamps down onto the electrode rods that come out of the back on some. So sometimes you'll see the brass and sometimes you'll see the aluminum or the stainless steel. But it connects, that's what connects to the transformers. Okay, it's usually spring connects. We don't usually have, well, most often we don't have wire connections there. There's a few burners that do, but it's not often. Okay, we've talked about electrodes already. I'm not going to get into that again. The arc of the spark, okay, is what contacts the fuel-air mixture, starting the ignition. Once I have fire, do I need my ignition anymore?
No.
No.
Okay, yeah, once I have fire, I don't need to maintain that ignition as long as I still have flame. So once I have flame, I can shut off my ignition. And I could continue to throw oil into the fire. And as long as the fire is maintained, okay, as long as combustion is maintained in the combustion chamber, I can continue my combustion process because the heat from the combustion itself will ignite the new fuel. Okay, now, the minute I have my ignition source, the minute I have an air problem, the minute I have anything out of alignment, that fire can go out. Okay, and I have to be able to sense if that fire goes out so I don't continue throwing oil into the combustion chamber. Okay, and that's what we have some safety controls, which we'll talk about in the next few days over. Again, this is basically what I was telling you about electrode adjustments. You have three basic adjustments. A is the distance between the 2 points. Okay? It's a very small measurement. It's all based on the nozzle degree and how many gallons of oil per hour we put in. Okay? Very small adjustment. An eighth of an inch and a 16th of an inch is not that much. B is the distance above the nozzle center line for our igniters. Okay? Smaller amounts of oil, smaller nozzle degree angle. By the way, that degree angle, again, remember, is the angle of the cone of the spray. Okay, we normally are anywhere between 9/16 to 5/8 inch, with the exception of a 45-degree angle, and that's ½ inch to 9/16. Okay, very, very small adjustments. C is the distance, the tip of the nozzle to the tip of the electrodes, how far in front it is. Okay, it's this distance right here, the separation from the tip to the tip of the nozzle. Okay, we're either at a 1/4 inch or an 1/8 of an inch. Okay, can anybody see problems making and keeping those adjustments?
Yeah.
Shake out of place.
Okay. Takes very stable hands, takes a lot of practice. So when your instructor in the shop says do this like 1,400 times, okay, and has you do it over and over again, please don't get upset with your shop instructor. It's for a reason. Okay, I want you to be able to graduate, go into the field, and be able to, with the person who you're working with for the first few years or first year, depending on where you're at in the field, I want you to be able to take it away from him and say, hey, let me try that. I can get it. Okay, that's the goal. Okay, so practicing this is the only way you can understand and make these adjustments, because it would be nice to have an extra 2 hands, but that's just not going to happen. Okay, so nozzle is electrode settings. By the way, this is one of those PowerPoints that if you haven't downloaded to keep for your own records, sometimes this chart is hard to find. Okay, it's nice to have this chart because occasionally this chart is hard to find. So I would recommend you download this PowerPoint just to have this table. Common problems. Our biggest problem with oil, when I used to have to go into the field a lot to check up on oil systems that aren't running right and 4 different technicians have been there, or the same technicians 4 times, the biggest problem we had with oil is wrong electrode adjustments. The gap is too large, or the electrodes are in the center of the oil stream. In other words, they're not at one of the outer portions of the stream. Okay, again, these measurements are extremely important. The other problem, cracked and dirty ceramic insulators. A crack in these insulators, no matter how small the crack is, electricity, the electric current will find its way through the insulator, and it will actually go to the metal on the metal holding the insulator, rather than try to jump across an air gap and create a spark. Remember, it always takes the path of least resistance. And the third problem, and this is very infrequent, could be a bad transformer. I don't see a ton of bad transformers. They last forever as long as everything else is right. Okay, now, how are you going to, when you come up to an oil furnace that's having a problem, okay, how would you look and see if it's the wrong adjustment? How would you diagnose that? When you come up to an oil furnace?
The flame?
Well, once I have flame established, remember that I don't need ignition anymore, right?
True.
So how would I find if there's a wrong oil adjustment? If there's a wrong electrode adjustment?
Maybe the BTU output?
Well, once I have a flame established, I don't need the electrodes anymore.
The nozzle?
What about the nozzle?
You still have I guess, residual oil at the tip, don't you? Or dripping oil from the
Let's
nozzle?
hold off on the dripping oil, but if I have a lot of carbon buildup on the tip of the nozzle, it's possible that could be caused by incorrect electrodes, because it could be sparking to the nozzle instead of to the other electrodes. So that could be part of my gap setting. Okay, what about the old idea that when you get up to an oil furnace that's having a problem, one of the first things you should do is pull that nozzle assembly and check the electrode setting just manually?
I guess you could do that. It would be time consuming, but...
Not that time consuming. You can pull that nozzle assembly in 5 minutes. Is it worth the 5 minutes to be sure?
Yeah.
Yeah. You're already on site. It's worth the 5 minutes to say, you know what, let's just check and make sure the technician who was here last actually did it right. There's something you're going to hear me say over and over again. Never trust the technician who was there before you, even if he's your best buddy. Okay? Might have been a bad day, might have been a bad end of the day, your service manager might have pissed him off. He might just not have been thinking properly. He might have pushed it out of adjustment when he put the nozzle back in. Everyone has days like that, and to just count on that it's going to be set up right is just a bad way to go about troubleshooting. So one of the best things you can do is any service call you go on, you want to check those electrode adjustments. It's worth the 5 minutes. What about the cracked or dirty ceramic insulators?
Making sure they're clean and not broken.
Well, you already have, when you're checking number 1, you already have the thing in your hand, right? Isn't it easy to check number 2 while you're at it?
Of course. Just check the entire thing.
Yeah, you already have the whole nozzle assembly in your hand. Might as well look at it. Bad transformer becomes a little bit more interesting to check. Okay, you either use a transformer checker, you use the old spark method, which I highly advise against, or you ohm it out. Okay, ohming out is the best idea. Okay, bad transformer. Will it always fail, or will it sometimes fail?
Very rarely.
No, I mean, if you have a bad transformer, when you walk up to the furnace, is it possible it's working?
Yeah,
Yes.
it could be working.
Yes.
Yeah, it could be a random issue. Okay, it could be happening when it's colder. It could be happening when it's warmer. It could be a random issue. By the way, those are the most difficult to find. Random issues. You're tempted to just start replacing parts, but you don't want to do that. Any questions on the common problems?
Negative.
Anybody else? Any questions on the common problems?
Nope.
Okay. Just want to make sure that those who have questions ask them. Okay, because common problems, this all comes back to what you're here to learn how to do. And that's to diagnose bad equipment. Okay. Just a quick 7 things on solid state. Again, don't want to beat it to death, but I do definitely want to talk. We definitely need to make sure that everybody is clear on the difference. Newer oil burners don't utilize these the old style ignition transformers. So when you come up to an oil burner, if you don't see the big square looking box sitting on top of the oil burner assembly, sitting on top of the blower, you have one of the low profiles. It's going to be a solid state transformer. Okay? The solid state igniter is much lighter. If you hold these in your hands, the old style transformer is going to feel like a brick. Okay, compared with the solid state one. Very light. The voltage output of a solid state igniter is typically higher than that of the conventional step-up transformer. Okay, it's a higher voltage. Okay, this is where we start getting to the 14,000 through 20,000. Higher voltage. I have a better spark. Okay, it can produce voltages between 14K and 20K. Okay, now, the reason why we like that, the higher voltage of the output, faster fuel vaporization. The higher the voltage, the higher the heat I have. So it's a much quicker vaporization of the fuel and the ignition. Remember, I cannot burn a liquid. Okay, solid-state igniters are not greatly affected by drop in supply voltage. Let me get back to that in a minute. Solid-state igniters use less electricity than ignition transformers do. Now, the grand scheme of things is the ignition transformer uses less than like 2 amps of power. Okay, they're not major sinks on electricity. But the solid-state igniters shut themselves off once flame is established. We'd shut the igniter off. Cannot leave it running all the time. What's your average supply voltage coming in from the power company to your house?
About 10,000 to 20,000.
Coming into your house. What do we bring into your house on line 1, for example? Supply voltage.
120?
120 volts.
Yep. What do we bring in on line 2?
220.
Now, line 1 to line 2 is your 220, 240. So on line 1, I have 120. On line 2, I have 120. Remember the old sine wave that I showed you?
Yep.
Okay, I have 120 up here, and I have 120 down here. Neutral is in the middle. So neutral is my 0 point. L1 is up here. L2 is down here. So if I take a voltage reading from neutral to L2, I have 120. If I take a voltage reading from neutral to L1, I have 120. If I take a voltage reading from L1 to L2, I have 240. That's how that works in your breaker panels when you have a double pole breaker. It's going from L1 to L2. Your single pole breakers for your lighting circuits, your plugs, your oil furnace are just going from neutral to L1 or neutral to L2. That's how we come up with our 120. Now, is it always 120?
No.
Everybody agree no?
Yeah, no.
Yeah, that's the correct answer. Now, does anybody know what the power company is allowed to do with voltages?
No.
Step up.
They're allowed at 10% in either direction.
Okay.
Okay, so I can, between L1 and L2, I can very easily have, instead of 240 volts, I can very easily have 250, 252. Okay, just like on a heavy power use day. Okay, like if you guys have a 100-degree day in August, okay, the power company is throwing all the power it can generate and buy from other power companies onto the grid. Okay, it's very possible in a urban area like, if we're talking like downtown Hartford, downtown New Haven, where there's a lot of power use, okay, we can very easily have a voltage drop that can drop that 240 volts between L1 and L2. We can very easily go down to 220. Okay, solid-state igniters aren't affected by this. Okay, but the traditional transformers, if I drop that voltage, I am seriously dropping my output voltages. Okay, And again, it doesn't happen often. Most often, our power companies are actually running over the 120 volts on line 1 and line 2. Okay, we're running very close to the 250 side of things these days. It's more efficient for them. Okay, but again, we can run much lower. Any questions on that?
No, sir.
Okay. So again, solid-state igniters, they will overcome that. Okay, again, they make an igniter tester. Okay, make sure you know how to use it. Okay, always when you buy something new and unusual and you buy a new toy to use to help your trade out, always read the directions. Does anybody know what the high voltage on your meter is?
No.
No, not at all.
Don't go over 600 volts.
Okay, that's good to know.
So you don't want to use your meter on a 10,000 volt transformer. Okay, bad things happen. Don't do it. Okay? Your meter leads are not rated for that much voltage, okay? And you also have to be careful of amperage on your meter leads. But always look at the manual that comes with your meter. It's always nice to know. Because sooner or later, you're going to come across a 720 volt rooftop unit. Okay. And some of the meters might have 800 volts, some of the newer ones. But just, again, be careful. Okay, solid-state igniter, lower profile. By the way, this device to the right of it that I'm circling, what is it?
No idea.
That's my primary control. Okay, we're going to spend a lot of time on this, but this is my entire safety, my sequencing for the motor, for the igniter, and over here there's probably an oil valve if I'm looking at this correctly. There's a wire that's coming from there. So everything on the sequencing of the oil burner comes from the primary control. Okay? It has everything to do with safety. Okay? You can't just run an oil burner by plugging it in and turning it on. Conventional igniter. Okay, we've talked about this one. The big box, it weighs a ton. It's like a brick. Don't drop it on your foot. Okay, this is an ignition transformer tester. Okay, it basically is it good or bad is what it comes down to. You hold the tester against the point here. Someone kill that phone or mute yourself, please. You hold the tester against the points, and this little light comes on, right, that light up there, that says test OK. It's either green or not. It tells you if the transformer is good or bad. By the way, if you turn this on, would I want my hand right there?
No.
Yeah, that's asking to get zapped. Don't do that. Okay. But the ignition transformer testers are nice to have. It's not an expensive tool. It costs probably about $150, and I think you can buy them for much cheaper on Amazon these days. Solid-state ignition testers, again, I still think the ohming it out method works the best. It's always helped me find the bad igniters. Okay, in all the time I was doing oil, I never had one of these. I used the ohm out method. It worked every time.
So I have a question. So if you want to ohm out this transformer, how exactly would you go about doing that?
Okay, let me erase my scribbles that are right there. Okay, first of all, I wouldn't have this ignition transformer on it, okay?
Okay.
So what I would do, and I'm going to go back one slide. Okay, this is the same ignition transformer that we had on the prior slide. Okay, so first I check my primary winding, so I'd ohm from there to there.
Yep.
Okay, I want some number other than 0. If I get OL the primary side of this transformer is bad. Then I'm going to go from there to there. I'm going to put one lead on this spring, one lead on this spring. What should I get?
You should also get some numbers, shouldn't you?
Is it going to be greater or less than the number that's on the other side?
Greater.
Yeah, because I'm going to have more windings because it's a step-up transformer. Should I have 0?
No.
No. If I have 0, I have a direct short. Then, let me change my pen color because that's just... Then, I'm going to take a reading from here to here. What should I get?
You should get 0.
No. If I take a reading from there to there and get 0, I have a short across it.
Okay.
You should still get some number, right?
No.
OL.
I should get OL. Remember, in a transformer, is there any electrical connection between the primary and the secondary side?
No.
So I should always get OL, ohming across the primary and secondary side. Now, there's one more reading I want to take. Can anybody tell me what it is?
The neutral?
I've already dealt with neutral.
The line 1 coming in?
No, I dealt with that. What about if I wanted to take a reading from...
Oh, ground.
Yeah. I can have everything else okay, but I could have a short to ground. So if I put a lead on one of the screws, not a painted surface, if I use one of the screws, put a lead on one of the screws and then to a spring of the transformer. Okay? Or to one of the leads of the transformer. By these readings, have I checked everything about the transformer?
Yes.
Yeah. So what if I get everything that I'm expecting on this transformer?
Then it should be good for use.
Okay, but the burner doesn't run. What am I going to check?
Check your wire connections.
That's a very good possibility.
The path itself, the entire path.
Well, I'm going to, honestly, if I get good wire, my transformer's good, I'm checking my entire ignition. Checking the entire nozzle assembly next.
Okay.
Or I've already checked my nozzle assembly, depending on what I'm there for. Okay? Because the ignition transformer directly feeds the nozzle assembly. So if I know I'm getting power into my ignition transformer, okay? If I know I'm getting good power here, if I know my ignition transformer ohms out properly, I now have to look at where that power is going. And again, be careful. You're dealing with 10,000 volts here. Okay. Questions? Did I answer the question on how you test these things?
Yes.
Okay. Any other question on that?
No, sir.
Okay. So, when we get back to our schematics, we are now at the point where we're starting to talk about, where we're starting to get to the point that we're going to start building our circuits. Okay, we've been leading up to with the basics of schematics, but now we're getting to the point where we need to start building our circuits. Okay, so our next step of our schematics is to start looking at things from a direction of what we're going to be seeing in the field. Okay, what are we going to be seeing as our basic oil burner parts? as our basic electrical parts on our schematics. Okay? Let me make these a little bit shorter. Okay? So we always start any schematic with our two sidebars of our ladder rung, because we're talking ladder diagram. Okay? We have our loads all here. Okay? So we're talking line and neutral. Okay? Get in a habit of labeling as you go. Then we have our transformer. Because again, we have a transformer in just about every oil furnace out there, or every oil situation. We have a transformer. Make yourself a symbol sheet. Keeps it very easy. You never have to wonder what your symbols are like once you draw them once. I'm fine with symbol sheets. Use them. I'm just not going to give it to you. Okay? So you drag in your transformer. Connect your transformer in. Okay? I have half my battle won right here. I now have my line voltage side and I have my control voltage side. Okay? Now, line voltage side. We haven't touched motors yet. I'm not going to go there today. Okay? So for the moment, I'm just going to use 2 light bulbs. Okay? Let me pull the line size down on this just a little bit. Okay? I'm going to use 2 light bulbs. Why do I have 2 light bulbs when I start talking about oil furnaces? Why do we have 2 loads on the line voltage side? What am I talking about?
Because we have 2 motors.
We have 2 motors. One is an oil burner. Where's the other one?
The other is
fan motor.
The fan motor.
Yep.
That's correct. The fan motor is correct. So I have 2 loads. Okay, on that side. Now, what do I have? Do I have any loads on my low voltage side?
Yes.
What do I got on my low? What do I got on as a load on my low voltage side?
Thermostat, right?
Is that a load or a switch?
Oh, sorry, no.
It's a switch.
So what do I have as a load?
A heater.
On my low voltage side. A relay coil, did somebody say?
Yep.
I knew I heard somebody say relay coil. Okay, so I have a relay coil. Okay, well, we know that's a load, so does it have to connect back to common someplace?
Yes.
Okay, so we connect that back to common. In an oil furnace, what do I have that's controlling my relay coil?
The thermostat.
The thermostat, you are correct. So, is it a heating thermostat or a cooling thermostat?
Heating.
Yeah, we need to know what's in the space. Okay, so we need to grab our heating thermostat. Okay. Do I have anything between a heating thermostat and my relay?
No.
Not in this case. You might occasionally. There might be a safety switch or two in here. But in the average oil system, your safety switch is all in that primary control. We're going to talk about that because this is actually contained in a primary control on most oil systems. So for the moment, we're just going to call this PC, okay, for primary control. We're going to label that thermostat, heating thermostat, and we're going to label this bulb, okay, actually that bulb is your burner. Okay? So we're just going to label that bulb burner. I'm going to label that bulb fan. Okay? Now, if I have a primary control down here that has a relay coil, what must I have up here?
Contactors?
The contacts connected to that relay coil. Is it normally open or normally closed?
Normally open.
Yeah. Okay, so if I have a normally open contact, yeah, we'll put it there. What's that contact labeled?
Normally open.
Anybody else?
Well,
If my relay coil is labeled PC, what does my contact have to be labeled?
Oh,
PC1.
Could be
Two.
PC, could be PC1, okay? The whole purpose is that I'm looking at a schematic with many contacts and relays on it. Like if I'm looking at an entire oil boiler or an oil furnace system that has a lot of additional contacts on it, I need to be able to identify what relay coil controls what contact. Okay, so that's why labeling starts becoming so important. Okay, so I have that. Does my burner motor have anything after it?
no, you need to connect it back to neutral.
Need to connect it back to neutral. Let's just draw my neutral line in here before we forget. And I didn't connect that one, so let's pull this over a little. Okay. So now I'm creating heat. What am I going to do with this heat?
Gotta move it.
Got to move it. So what do I have to energize sooner or later in here?
The fan motor.
man.
Okay. So we know a motor. We've already got it by this point that the motor I'm going to have to pull over to neutral, right?
Yes.
Okay. Now, how am I going to control this fan?
Through a relay coil? Or a relay
Let's
contact?
go. What was that? I'm
switch?
sorry.
A relay contact?
Well, okay, let's go down the relay contact because you're not entirely wrong in some cases. What if I was using a relay contact? What would control that?
The coil.
Where would I have the coil?
The coil would be on the 24 volt side.
Yeah, but where would I have it?
After the thermostat. No, after the burner.
Okay, you're not entirely wrong, okay? That's why I wanted to go down through this. There's two different ways to control the fan. And again, if you don't get this the first time I run through it, we're going to talk about this more in the future, okay? So all of those who aren't following along or need more on this, we're going to talk about this more in the future. There's two ways to control this fan. Okay, first of all is by a temperature sensor inside the ductwork right over the furnace, okay? Basically, it's called a fan switch, a fan cycling switch, combo fan switch, all of those things. What it does, it senses the temperature of the furnace, and when the furnace temperature gets high enough, it turns on the fan. Okay, now if you think about this thermostat right here, okay, that I have labeled cooling thermostat, what happens when the temperature rises and you have this thermostat someplace?
It closes.
Right. So if I used that cooling thermostat right here, would it turn on my fan if the temperature went up?
Yeah.
That is the traditional way that we have been turning on fans in oil forced air systems for 40 years or more. Okay? It's basically fan limit, it's called. Fan limit.
Oh, the fan limit switch. Okay.
Yes. Okay, for those of you who've already had the gas heat term, you've seen this before. So for traditionally, for close to however many years oil's been around, this is how we've been turning on and off fans on oil forced air equipment. Now, having said that, there's a new way that the engineers of today, okay, on the new modern equipment, have started to turn on fans. Let me see if I can do what I just meant to do. Okay. If I take this fan limit switch out,
Leave that. Leave it.
okay, and if I put in a contact, like you were going down the road with the contacts, which it wasn't wrong. This is why I sort of wanted you to go a little bit further with it.
Mm-hmm.
Okay, if I go down the road with the contact, okay, and if I label it, if I just come in here and label it fan contact, just for FC, and then if I came down here after the thermostat, exactly like you said, okay, and I'm going to grab a copy of basically that, my relay coil, which didn't quite copy really well. Sometimes that happens. So we'll just finish off that relay coil real quick. Okay. And we will shove that all over to its side. Put it right under that other one. What do I have to do about the right side of this relay coil?
You have to bring it back to the 24 volt side.
Common, yeah. The side of any 24 volt transformer that's not connected to the thermostat, okay, is known as common. You'll see us use that term quite often. It's common. Yeah. So common and neutral are basically the same thing, but on the two different voltages. Okay. Do I want my fan to come on as soon as the thermostat calls for heat?
No.
Why?
Because there's not enough heat in the heat exchanger yet to blow it through the house.
What will the customer feel if the fan comes on immediately?
Cold air.
They're going to feel a lot of cold air. So we want our furnace to heat up before we start blowing air around the room. Okay, so what I can do, and what is being used more frequently as time goes on, okay, we're using a time delay relay.
Oh, okay.
Okay. So what we do is we put in a time delay relay, and we set it to however long the manufacturer says. By the way, notice my wording on that. Forever long the manufacturer says that it takes that furnace to heat up to a safe temperature. Okay, so there could be a delay of a minute, minute and a half, usually not more than that. But, I mean, there's a delay for this furnace to warm up, and then it will turn on the fan control relay, close the contacts on the fan, and energize the fan. Okay, any questions on this? Because I actually went pretty far ahead of where I wanted to go with this today.
No, no questions.
Anybody else?
Negative, sir.
Okay. I'll leave this here for anyone who wants to take a picture of the screen or take a screenshot. We're going to do this diagram again. I don't expect you to memorize it. But what I'm trying to do is show you where we are building to as we're starting to talk about our sequencing, as we're starting to talk about our schematics and our electrical. Okay, because this is the top one that I'll pull back up on the screen in a minute is our basic oil burner diagram. Okay, so my top one that I did originally is that one right there. That is my basic diagram for oil heat. We still have to talk about the burners and we still have to talk about motors because schematics, really, we don't want to show circles. We want to show what type of motor and everything they are. But between this diagram and the other one, we've talked about where we're going with schematics initially. There's more that we're adding on, but that's where we're going. Any questions?
No, sir.
No.
I have a question about the schematic of the day.
Yeah.
What do you mean exactly about a second switch will bypass the second bulb in the series when closed?
Okay. I don't want to totally give away the answer because I want you to think about it.
Like what you want the switch to do more specifically?
Well, it's bypassing. So it's basically taking the electric circuit around that second bulb to take it out of the circuit.
To take that bulb out of the circuit.
Yeah, remember, electric will take the path of least resistance.
Yeah.
Does that make sense?
Yeah.
That clears it up for me, because I was going to ask the same thing.
Okay, and I know somebody sent me an email on it too, and I forget who sent me the email on it. But basically, electric takes the path of least resistance. Now, the thing to be very careful about is which leg of the circuit you're taking that bypass to.
Yeah.
Is it going to be line or neutral? And don't give the answer on the call, okay?
Okay.
Okay, so just think about the sequencing.
Got it. Thank you.
Okay, any other questions? Gentlemen, that's all I have for today. Okay, you guys have a great day. There's work due. Please get things turned in.
Thank you very much. You